Hi, I'm Alan Bowling in the Department of Mechanical and Aerospace Engineering at the University of Texas at Arlington. This presentation is a three-part series on derivatives and integrals in dynamics. So let's get started. Okay, so in an earlier presentation on 2D vectors, we were looking at the problem of moving from this point to this point, and the distances involved if you move along the street, or if you were to simply fly over all these buildings and move straight to that point. So just go straight as the crow flies right over that to the next point. And then in a subsequent presentation on systems of equations in engineering, we also looked at our friend. We said we might have a friend who also wants to fly over all the buildings and go from this point to this point. And if you look at those two, you might say, well, there's a chance that we can collide here in the middle. So in the systems of equations in engineering presentation, we actually found the coordinates of that point where we might collide. But if you just look at this problem and think about it, you can easily say, well, what if we are flying kind of very slowly along this path, and we're just moving very slowly like this. But what if our friend, he gets in the air and just gets moving and goes very quickly over here? So you can imagine that our friend would pass that green point, the intersection point, faster than we would get to it. So by the time we got to the intersection, our friend would be gone and we wouldn't collide. So if we really don't want to collide, then let's figure out the conditions that would cause us to collide, and then we can avoid that situation. So what's going to be required of us is to look at the speed at which we move along this path from our starting point to our ending point, and see what speeds we're moving at and if they're sufficient to make us collide. So let's do that. Okay, so now we want to go into the math world. And when we go into the math world, we want to simplify things. So we've gotten rid of all the trees and everything else again. And now we're just labeling our points A to B, which we're going to fly from. And our friend is going to fly from points D to C. So if you can recall an earlier presentation we did on systems of equations in engineering, we set this up as a system of equations using lines, equation of a line to describe the paths from A to B and D to C. So when we did that, we used our directions east and north, and we said, okay, from point A, we're going to measure the distance in the east direction by the variable y, and we're going to measure the distance in the north direction by our variable x. And we took each one of these points and we gave them a distance. So A was 0, 0, our origin, and C was 4 units in the x direction and 0 in the y direction. B was 4 in the x direction and 4 in the y direction. And D was 1 in the x direction and 4 in the y direction, or north and east directions. So then our path went from A to B and from D to C. And we actually found out the distance to this intersection point, which was 16 over 7 in the x and 16 over 7 in the y. So using this information, we're able to get two equations to describe these two lines. So this line here was defined as x equals y, and this line here was defined as x equals minus 3/4 y plus 4. So that's all good, but those two equations only contain position information. They just describe the path. They don't really tell us how fast, they don't let us get any information about how fast we might be moving along those paths. So we can include that information or allow ourselves access to that information by doing what we call parameterizing. So for this red line, we're going to parameterize by time. So our equation is now going to become that, x1 of t equals y1 of t. Now that doesn't change the path, but it lets us mess around with the speed that we're going to move along that path. So it says how our position as a function of time. We can do the same for the blue line, and we use a different line, and we can parameterize it with time by using these variables x2 and y2. Now we haven't changed the geometry of that line at all, but we just said, okay, now we're going to look at our position change as a function of time. And I use x1, y1 on the red line and x2, y2 on the blue line to allow us to move at a different speed than our friend along their line. So we actually didn't change the paths. Now we've just put in some information that allows us to adjust the speed that you are moving along each of those lines. So we give the position as a function of time. So how do we get the velocity out of this? How do we get information about the velocity out of these equations? Well, let's look at that next. Okay, so now we're going to go completely into the math world. So there's no more map anymore, and we're just going to look at our equations. So we had two of these guys. x2 of t is equal to minus 3/4 y2 of t plus 4. So how do we get velocity information out of these equations? Well, velocity is the derivative of position. So we can take the derivative, which we designate as d over dt, of both equations. And if you do that, and you remember how to take the derivative of things, you can just express these derivatives in this way, and this guy will equal dx2 dt equals minus 3/4 dy2 dt. And those derivatives tell us the rate of change of position, or this one tell the rate of change over position with time. So this tells us the rate of change of x1 with respect to time. So that's the velocity in the north direction on our path. And this one tells us the rate of change of y1 over time, which gives us the velocity in the east direction. And likewise for our friend on his path. So all of these quantities here are what we call velocities. So these are all velocities. And the interesting information that we get is that in order to stay on the path, our path, our velocity in the north direction has to be equal to our velocity in the east direction. And for our friend to stay on his path, his velocity in the north direction has to be less than the velocity in the east direction, because it's multiplied by minus 3/4, which is less than 1. It's also negative, so that means he's going to be going in the negative east direction. So how do we use this information to solve our problem? Well, we're going to take a look at that in part 2. So in summary, in this presentation we learned how to parameterize an equation of a line to incorporate the speed of movement along a line. So we're able to parameterize distance, a variable that describes the change in distance in terms of time. So that tells us how our position changes with time. And if we have that description, we can take the derivative of it to understand how to get a description of velocity, which tells us the rate of change of position with respect to time. So please watch part 2 to see how we will use this information to analyze how fast we are moving along, how fast we and our friend have to move along this curve, along our paths, to have a collision. Thank you.